Now we looked at amines here, C3 amine and a C7 amine. We can take those same amines here, and by reacting with the acid reacts with the basic nitrogen to form a ionic compound now. So this ionic compound remains soluble in water even though it has a longer carbon chain. So the C7, whereas this hydrogen bonding was insoluble in water, we turn it into an ionic compound, and that keeps it soluble in water. So same thing with the acetic acid, or with the carboxylic acid up here. We have our C2 and C6 carboxylic acids. We turn that into an ionic compound, or increasing the melting point dramatically, but we're also making it soluble in water. So making it as an ionic compound makes it soluble in water. Another property that we can look at is surface tension. Surface tension is the tendency of a liquid to be pulled into the bulk of the liquid. What this does, it minimizes the surface area of the liquid as much as possible. It also creates a type of skin on the liquid that resists penetration. So the stronger the force is that pulls the liquid into the liquid, the stronger the surface tension will be. So surface tension allows us to float things on water, such as paper clips, allows insects such as water striders to float in water. It causes water to form a teardrop as it's falling, which is trying to go for a spherical shape, which would have the smallest surface area. Friction as it falls turns that spherical shape into a teardrop. In the International Space Station, water will form a sphere instead of a teardrop. So as we increase our intermolecular forces, we're going to expect surface tension to increase. So if we have an ionic liquid, we're going to expect the ionic liquid to have a higher surface tension. We're going to expect a hydrogen bonding liquid to be higher than dipole-dipole, and dipole-dipole will be higher than dispersion forces. Capillary action is the tendency of a liquid to climb up a narrow tube. This is based on adhesive forces between the liquid and the material of the tube. So if the adhesive forces are strong compared to the cohesive forces of the liquid itself, then the liquid will climb the tube, and it will be higher on the side of the tube than it is in the center of the liquid. The curved surface is called a meniscus, and that curve can be either high in the center or low in the center. So if it climbs the sides because it has strong adhesive forces, then it will be low in the center. So that will be a concave meniscus. If it's low on the side, high in the center, that means the adhesive forces are weak compared to the cohesive forces. That would be mercury inside glass. The mercury bends down along the glass, and we'll have a convex meniscus. Whereas liquid, water will climb up the glass. Water climbs the glass. Water has strong adhesive forces with glass, and mercury has weak adhesive forces with glass. So evaporation, condensation, vapor pressure of compounds. So a liquid has a tendency to allow some molecules to escape into the gas phase. So the molecules in the liquid will have a range of velocities. It takes a certain amount of energy to pull away from all the intermolecular forces of the liquid and escape into the gas phase. But depending on the temperature, some molecules will have that energy that can just escape into the gas phase. If gas is an open system, such as a glass of water that's open. The water can escape into the gas phase, and the gas can blow away the water. So the water will just keep evaporating away until we finally have no water left. If it's a closed system, a closed bottle, water will escape from the liquid to the gas phase. That will build up a pressure of water in the gas phase. That water in the gas phase will be colliding with the water liquid. Some of those water molecules in the gas phase will be captured by the water liquid and recondense. As the amount of water in the gas phase increases, the rate of water being captured by the liquid and condensing again will increase also, until finally a certain pressure of water is attained in the gas phase that remains stable. That means the evaporation equals the condensation. And the amount of pressure of water in the gas phase is called the vapor pressure of the water, which is temperature dependent. As we increase temperature, we're allowing more water to escape into the gas phase, so we'll increase the pressure of the water. And when we look at different materials that evaporate easily are called volatile. Materials that do not evaporate well at all are called non-volatile. The volatile liquids have low intermolecular forces. The liquid is able to escape easily into the gas phase. The non-volatile liquids have high intermolecular forces. These molecules cannot escape easily into the gas phase, so they're held strongly into the liquid phase. So high intermolecular forces will be non-volatile. So that's why when we have a liquid ionic compound, we don't have too many of them, or we can melt a typical solid ionic compound. Ionic compounds have very high intermolecular force, so even when we have it in a liquid state, they do not volatilize easily. Water, which is hydrogen bonding, has a relatively high volatility. It evaporates on us. Acetone, which is dipole-dipole, has a higher volatility. Acetone evaporates noticeably faster than the water does. And then propane, which is nonpolar, dispersion forces only, has such a high volatility that it's already a gas at room temperature, and we have to take it to high pressures or low temperatures to turn propane into a liquid. All this process of going from liquid to a gas phase is endothermic. We have to give enough energy to that molecule to escape the intermolecular forces, so that molecule is taking that energy away from the liquid. So it's an endothermic process. The reverse process of condensation, turning the gas into a liquid. Now, as the gas collides with the liquid and sticks there, it's giving its energy to the liquid. It's an exothermic process. So evaporation is endothermic and condensation is exothermic. Now, if we have a container, a closed container with a liquid in it, a certain amount of the liquid will escape into the gas phase. It will increase the pressure of the gas phase up to a point when the condensation rate equals the evaporation rate. So when condensation equals evaporation, we'll have a certain pressure in that gas phase that came from the liquid. This is called the vapor pressure of the liquid. Vapor pressure is temperature dependent, and vapor pressure will increase as we increase temperature. Since evaporation is an endothermic process, as we add temperature to the system, it will allow more of the liquid to evaporate, increasing the vapor pressure of the liquid. And we know that water can evaporate at room temperature, so it can evaporate, about 25 degrees room temperature. But water has a special temperature at which it evaporates also, which is called the boiling point. So when we get the temperature high enough, such that the liquid can pop into gas inside the liquid, so we got bubbles of that liquid forming as a gas inside the liquid. Now it's boiling. This occurs because the vapor pressure of the liquid is now greater than all the pressure on top of that liquid. So it's greater than the atmospheric pressure and whatever liquid weight is on top of it, so the liquid can just burst directly from liquid into gas phase, so it's pure gas. So for boiling water, we've got pure water vapor being formed inside the water as bubbles. So atmospheric pressure can change. It does change with elevation. So our local boiling point changes depending on what elevation we're at. So the boiling point of water in Denver is different from what it is in Santa Monica. So what we often are comparing is what's called the normal boiling point. Normal boiling point is when we're at 1 atmosphere of pressure. So that would be Santa Monica under good weather day. So sea level under good weather, we have 1 atmosphere of pressure. And when a liquid boils, that's called the normal boiling point. So it boils at 1 atmosphere for normal boiling point. But different regions can have different boiling points because it has different pressures on top. We can increase the boiling point by using a pressure cooker, by increasing the pressure inside a container. So it's now cooking at a higher pressure, which would be a higher boiling point, a higher temperature. So for a liquid to burst into the gas phase, it has to exceed all the intermolecular forces. So it's going to be harder for this to do it when we have stronger intermolecular forces. So stronger intermolecular forces will give us higher boiling points. So high boiling points will equal strong intermolecular forces. Strong intermolecular forces will equal higher boiling points. And if we have low intermolecular forces will mean that we're going to have higher vapor pressure, and the compounds will volatilize easily. So we'll have volatile compounds when we have low intermolecular forces. So this is a graphic representation for vapor pressure. If we start off with none of the liquid in the gas phase, then all we're doing is evaporating some molecules into the gas phase. As you get some of the gas phase molecules can now, as they're bouncing off the liquid phase, they can get stuck on the liquid phase. But when we have equal rates of evaporation and condensation, then we have a set pressure of that liquid in the gas phase, and that's called the vapor pressure of that liquid. And different compounds will have different temperature effects here. The graphs up here shows a range of kinetic energy or velocities of molecules. So their vertical axis is abundance, and their horizontal axis is kinetic energy. So if there's a certain amount of energy there to overcome the liquid force, the intermolecular forces, a certain fraction of the liquid can overcome that and escape into the gas phase. Whereas a majority will not have that energy. As we increase temperature, so T1 here is a lower temperature than T2, so as we increase temperature, we're pushing this spread toward the right, lowering the peak as we populate higher energies, but we're also getting a higher range of molecules, higher fraction of molecules that can escape into the gas phase then. So 2 liquids here, water, which is hydrogen bonding, and ether, which is a weak dipole-dipole. So at 0 degrees Celsius, they'll both have a very low vapor pressure. But as we warm it up, we get up to 35 degrees Celsius, noticeably warmer than room temperature. The water vapor pressure has not gotten very high yet, but the ether vapor pressure, being a weaker intermolecular force, has noticeably increased.